All right, so it looks like we're live, so let's get started. As I promised yesterday, we're going to round off with a discussion on one more NIM variant. And I think there are like literally hundreds of these. So of course, it's going to be out of scope to try and be comprehensive here. But we've been talking about Fibonacci NIM for the last couple of sessions. And I just want to do a different variant here, again, guided by the book, actually. So if you're looking or following along, then this is actually the last game that's discussed in chapter 0 on impartial games. And I'm not completely sure how to pronounce the name of this game variant. It seems like it's called Width of NIM. The spelling is WYTHOFF. And I have no idea what subset of those letters is silent. So I actually prefer calling it the Queen's Game because that's it's effectively equivalent to a game that you can play with a queen piece on a chessboard. So I'm going to come to that in a minute. And just to save myself potentially pronouncing this wrong all the time, I might sometimes just call it the Queen's Game instead. But anyway, so what does the game look like? Here is the setup and the rule set. So here, instead of an arbitrary number of heaps as in NIM or a single heap as in Fibonacci NIM, we actually have exactly 2 heaps. So that's the first thing. And now what's the other aspect of the variation? Well, basically you have to still remove at least one stake or token on your turn. There is no passing, but you can now remove K tokens from either one of the piles or both of them. So that is something that you're typically not allowed to do in NIM. So in every move, you can remove K stakes from one or both heaps. All right. Why did I say that it sounds or it can be recast as a game played on a chessboard with a queen piece? So imagine that you have a chessboard. Let me see if I can get a 8 by 8. Not that it's important, but all right. So you have a chessboard and a queen starts somewhere. With some position on this chessboard. Now, in each move, the player can move this queen, but only south, west, or southwest. Okay. Or if you're directionally challenged like I am, let me just say down, right, or basically diagonally like that. Okay. Actually, I don't know if saying down and right is worse because of that's my right. I hope that that's, I think that's universal. Okay, but you get the point. So basically you have this corner here. I think this is decidedly the bottom right corner. Actually, yeah, I mean, it really doesn't matter as long as you fix one of the corners and you decide that you're going to move towards it. So I think by convention, it's either the bottom right or the bottom left one, but it's really not important. The idea is that once you fixed a corner, you're kind of stuck in that quadrant in the sense that the permitted moves only allow you to move towards that corner. So you have to get closer to that corner in terms of, let's say, the Manhattan distance. I think that's a fair thing to say. So either your X or your Y coordinates are improving as you move. But because these are queen moves, as opposed to say knight moves or whatever, the amount by which you reduce your X or Y coordinate or longitude, latitude, however you want to think about it, is either that you affect exactly one of them. So you stay on the same horizontal or vertical line and move further along on the other one. So that's like picking up a certain number of sticks from one of the piles. Or you make a diagonal move, which means that you are shaving off the same amount from both the X and the Y coordinates, right? So that's the spirit of the rule here. And so if it's easier to imagine it with a chessboard and a queen piece instead of two piles of sticks, you're welcome to switch to that sort of visual. It doesn't hurt, it's exactly the same game. All right, so what do the winning states look like here? I think there's a very pretty characterization in terms of two sequences called, again, I'm probably butchering the pronunciation, but the sequences are called Betty sequences, not to be confused with Betty. I think there's an extra A in here. And I don't know how to account for that in the pronunciation. I'll come back to what these sequences are after working through a couple of examples. But I hope that this point that the rule set is clear. And the win is the usual, we are doing normal plays. So it's the player who doesn't have any valid moves left is the player who loses. So in particular, if you're already at the bottom right or at the target square, particularly when both heaps are empty, then the player who is facing that position loses. Okay, so let's, I think, analyze a couple of examples before trying to getting into and sort of characterizing the winning states. But let me also just say that some of the trivial losing states zero, zero. Some of the easy end positions would be zero and any non-zero number of stakes in the other heap, or an equal number of stakes on both heaps. So hopefully it's clear that these guys are immediate wins for the player who starts there. But let's, again, for the sake of just example and getting some practice, what about 1, 2? So think about what the first player can do in terms of possible moves. So you could do 0, 2, which is an N. You could do 1, 1, which is again N. Or you could do 1, 0, which is again an N, right? So you have altogether 3 sticks spread one on one heap and 2 on the other. So you could either empty out the first heap or the second one, but those are both immediately losing for the current player, for the player who's playing at 1, 2. So if the player wants to leave one of the heaps non-empty, then the only way to do that is to remove 1 stick from the second heap. But that unfortunately takes you to 1, 1, which is a situation where both heaps have the same size. So that's also a win for the other player. So basically, there's really no way that you can win from here. So this is an example of a P position. maybe worth doing another small example. Say you have 3 and 5. It's starting to look like Fibonacci again. But I think as far as I know, there is no direct connection with the Fibonacci pattern here. So with 3, 5, well, what happens? I'm not going to enumerate everything here, but let's look at some of the possibilities though. Again, if you try to remove, let's say, the same number of sticks from both piles. So let's say you go down to here, 2, 4. But no point in going here. So what about 1, 3? Here you're going to first get to positions like 1, 2, 0, 3. So all of these are ends, although you have a P sitting here, right? And so that's going to be N already for that reason. Today I'm wondering if I can make a more general claim about all the children of 3, 5, but I don't see like a sweeping way to do it. With 2 and 4, for example, what do we get from here? Let's zoom in a bit there. Again, I'm going to ignore the ones that are easily N. If you empty out one of the heaps, or if you remove 2 sticks from the second one, all of those cases are N's. The more interesting ones, I guess, when you remove 1 from each. So you get 1, 3, which we have already seen to be N. What else can you do? You could try and remove 2 from, well, if you remove nothing from the first and 2 from the second, that's not a good idea. But what if you remove 3 from the second one, you get 2, 1, which, well, this we know is a P. So this again is going to be an N, and so on. Okay, so some part of this, I think you can manually check, but I believe it turns out that all the children that you get from 3, 5 are actually going to be N. So this is another of those 3 positions, and you can sort of keep going in this fashion. But in the interest of time, maybe let's now think about some of the principles. And I'm not sure if you want to identify patterns, but there's also sort of a handy list of some of the early P positions. So this I'm going to leave as an exercise to sort of complete for the sake of practice. But it turns out that if you dig just one layer deeper into most of these positions, it's quite evidently all of them are N. So I'm debating whether I want to write down the list of some of these examples in case you want to spot some patterns. Let me put down a few of them here. Okay, so let me say that if you stare at this, maybe there are a couple of things that just emerge by looking at the numbers, but let me see if I can state a couple of principles which seem pretty intuitive and if we can justify that. So if you have two P positions, say A comma B and B comma Q, then A, B, P, and Q are all distinct. So this is sort of my first claim here. So why is this? Suppose not. So suppose, for example, you have AB, and for instance, you have, say, B comma A. How would this be a problem? Well, between B and P, one of these numbers is, well, I mean, I want to say that you should be able to go from one of these states to the other one. And that would kind of negate the idea that both of them are P, right? Because remember that a P state cannot have a P child, right? So one of the things that you could try and do is to change either P or B to an A, right? And that's going to be feasible if either P or B is larger than A. Maybe a cleaner way of writing it is to say either P is greater than A or B is greater than A. Then in fact, in these cases, you can actually directly move to, sorry, I think in these cases, I was trying to move to AA, which is that's an N position, so that's not what I want to say. I want to say that you can actually move from AB to PA, right? So when does that make sense? So sorry, I think I got distracted for a moment there. So, so in this case, it's actually if B is greater than P, then make this move. And if P is greater than B, then move from PA to PA. So I hope that makes sense. I'm not sure why I was trying to equalize, because that's something that you can probably do under some situations, but that just gives you an existing N child, which is not what's relevant to this argument. So here, what you can do is basically go from one of these states to the other one. My numbers here are flipped, but notice that the heaps are symmetric, the order doesn't matter. So AP is morally equivalent to PA. And therefore, what we have is that if two P positions share a number, then that would end up being some sort of a contradiction, because it would allow a P state to be reachable from another P state. Yes. So that's just something that we don't allow. And the second property I want to talk about when it comes to these positions is that if you look at two different numbers, two different pairs that have P positions, and you look at their differences. So let's say this here is X and this is Y. So this is the absolute value of the difference between A and B. So if we have two P positions, AB and PQ, and we look at the differences in the sizes of the heaps in both of them, then what do you think we can say about these two differences? I want to claim that these differences are not the same. And again, this is reasonable because if you have the exact same difference in two different P positions, then just like last time, one of them becomes accessible from the other one, right? So if I have, let's say this is AB, and so this is the difference here, and now you have P and Q with the exact same difference. So what you do here is look at the smaller of the two numbers and look at which pair has a larger, smaller number, right? So in this example here, you see that A is smaller than P, right? And so I claim that AB is accessible from PQ. And that is true because essentially, if I subtract P minus A from both columns, right? Okay, let me pretend that I'm taking it off from the bottom because that's an easier visual, I think. Then really what you're left with is P becomes A because you've removed P minus A from P, yes? And Q will become B because the difference between A minus B and P minus Q is exactly the same, right? So if two positions have the exact same delta, the exact same difference, then again, one of them becomes reachable from the other. And that's something that we basically don't allow. Okay. So that's really two key properties of this collection of numbers that you see here. Again, the positions are symmetric, but it's kind of useful to write down these positions with a smaller number coming first and the larger number later. And that's essentially our knowledge base of the P positions, a few starting examples here. And just as validation, you can see that you have one appearing on the left, nowhere on the right. Then you have 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, right? So each of these numbers appears one at least so far. So that's really more of a sanity check to make sure that I didn't make any mistakes copying down these numbers. And you can also see that if you enlist the differences here, that they're basically growing. So here you have a difference of 1. Here you have a difference of 2. Here it is 3. Here it is 4. Here it's 5 and 6 and so on, right? So we can't afford to have the same between two p positions. So it's in the way that these positions are currently written out, you can just see that the differences are steadily growing, right? So so just to back up a bit, what we did so far is, well, after introducing the rule set and listing out some of the trivial positions, we looked at a couple of examples. And although I don't think any patterns emerged from the examples necessarily, I skipped a bunch of manual labor to just put down the list of some of the initial positions. And if you stare at these positions, maybe the two claims that I made would actually pop out. But the claims are also reasonable from the point of view of basically inferring them directly from the rule set, right? So if you have two pairs that share a common number, then the idea is that one of them can be morphed to the other one. So you don't touch the common number, but you end up modifying basically the other coordinate to match. And I think in the chest visualization, this is actually cleaner. I don't know why I was being tricky about this when I was discussing it, but basically what this is saying is that if you have two positions that either share a row or a column, so the second position is either on the same column as the first one or on the same row as the first one, so this being the first position, then basically you can clearly snap to the starting position by making moves along the common row or column, right? So I guess that's it's a much shorter way of saying what I was saying earlier by rambling. So hopefully this is now easy to remember. The other claim is that you don't have same differences between two numbers in any of these p pairs. And again, that's fairly easy to visualize as well. If you do have the same difference, then depending on which is the bigger pair in terms of the smaller number being larger, you just knock out the difference between the two smaller numbers. And again, you can go from one of these positions to the other one. So you have a p position with a p child, again, something that's an immediate contradiction, okay? So that's what we have so far. And now at this point, I'm not going to say much more in terms of trying to prove anything, but I will make a claim about what these numbers look like. So if you think of these as number sequences and call this AI, BI, again, with the convention that AI is the smaller of the two numbers. So the left-hand column is one sequence, which goes 1, 3, 4, 6, 8, 9, and so on. And the right column is another sequence of numbers, which goes 2, 5, 7, 10, and so on. Then it turns out that the nth element of the left-hand sequence is given by n times p floor, and the nth number in the second sequence is given by n p squared, and again floored. This is where phi is the golden ratio, so that's 1 plus root 5 by 2, and so these are called complementary Vieti sequences. Again, I hesitate to mispronounce this name, but We'll live with it. And the complementary in this name is basically to capture exactly the two properties that we talked about. Well, okay, maybe I should not say exactly in the sense that one of them, so complementary involves two aspects here. And let me list out both. One is that the sequences have no intersection. So this is something that we did say was our first claim, that no number appears in both sequences. Now, the second claim here is that the union of the sequences is the set of all positive integers. So that's basically to say that no number appears in both sequences, but every number is covered. So the other way to combine these two properties is to say that each number, each positive integer appears in exactly one of these sequences, right? And it's not, there's no forcing on which sequence the number should appear in. So this is not the only example of a sequence that satisfies this property. But in general, you could define these sequences using this sort of a pattern that we are seeing here. So you can take an irrational number R and basically look at this sequence here. And this would be an example of a single Beatty sequence. So this is, I should probably emphasize that R is a positive real number, but we really do need it to be irrational. So if you look at, so this sequence is basically determined by R, and let's denote it BR. And it turns out that if you have two sequences, BR and BS, they're complementary if 1 over R plus 1 over S equals 1. And you can check that that's actually true for R equals P and S equals P squared. That's an easily verifiable exercise in computation, so I won't drill down on that. But these are all pretty much statements of fact that I'm making here without further justification. Of course, this right here is a definition, so there's really nothing to prove. But the two claims that I'm stating without proof as well. First of all, that this is indeed the formula that determines the nature of losing positions in Wythoff-Nim. The fact that the Beatty sequences driven by the golden ratio and the squared golden ratio actually give you the numbers of interest here. That is something that definitely requires an argument. And I was able to trace it back to, I think, one of the original papers that describes it. It's also linked to on the Wikipedia page, although I think the game sort of came to attention when, predictably enough, Martin Gardner talked about it in one of his columns. But coming back to things that I said without justification is also this idea that the sequences are complementary if 1 over R plus 1 over S is 1. That's also something that's sort of left as an exercise. Now, Also, because these are now complementary, which you can check by checking that when R is P and S is P squared, you can check that this condition is satisfied. We also have that every number appears exactly once in both of these sequences, which is, well, exactly once you account for both of the sequences together. And that's not how we stated our claims about this sequence. We did say that a number cannot repeat, but there's nothing we said which implies directly that every number must appear somewhere in the sequence. And so another little piece for food for thought is whether that's something that can be deduced from our other claim, which is natural from the game rules. But can you deduce from the second claim instead of appealing to the BT sequence machinery? Can you prove directly that every number must appear in one of the coordinates of a P position? So I'll leave you with that little puzzle here, and we are almost on or over time, depending on how you look at it. So let me pause here, and I'll also say that this does bring us to the end of chapter 1, well, or chapter 0, actually. We haven't really been working through exercises very much. Many of the exercises are basically additional practice to sanity check that we are on the same page with respect to the definitions. But I think some of the problems are more non-trivial than that. So if you're following along, and especially if you have the book handy, I would definitely recommend taking some time, at least taking a look at the exercises and maybe identifying a few that you find interesting to work through. I think it would be a great way to sort of recap the material. And that's basically all we have to say in terms of these discussions from this chapter. Like I said last time, we'll be moving on to a game called Geography and variants thereof, starting from tomorrow. And that will take us to chapter 1 in the book if you're following along. It's a relatively short chapter compared to the one on impartial games, which had several ideas. So this is probably that we will get through in a couple of sessions. So I look forward to seeing you then. And as always, thanks very much. We will stop